Welcome to the next lecture in the series of lectures in biochemical engineering. Today we are going to start discussing immobilized enzymes. So, the enzymes that we discussed in the previous classes are kind of enzymes which are mobile, we can call them mobilized enzymes, so to say. So, these enzymes are in the liquid phase. This was something that we are discussing at the end of last class. So, these enzymes are in the liquid phase, the substrate is in the same phase, and they are swimming around, sort of floating around and then reacting with the substrate. So, today we are going to discuss immobilized enzymes, which is that the enzyme is immobilized in a certain phase and the substrate is most likely in another phase. Now, as a prelude to this, if you remember at the end of the last class, we started discussing what is known as heterogeneous enzyme catalysis. So, as opposed to homogeneous enzyme catalysis, which is what we did in the last 5 lectures. So, that is where the spirit of immobilized enzyme lies, which is the case that the enzyme is in a certain phase, solid phase or something, immobilized, and then the substrate is in another phase. So, let me show you how immobilized enzymes look like. So, this chapter that we are starting today is enzyme immobilization, and there are several methods of immobilization that we will briefly discuss before we go on to the understanding of the process. So, there are chemical methods as well as physical methods. Now, so this is what you see on the screen is an example of a chemical method, where this enzyme that you see over here given by E shown here is covalently attached to the matrix. So, this is a matrix, and this matrix is typically water insoluble. Why is it water insoluble? Because for the enzyme to remain in that state, the matrix should not dissolve into water. If it dissolves, then the immobilization would all be gone. So, if you want the enzyme to remain immobilized, this has to be a water insoluble matrix. So, this is a chemical method. Why is it chemical? Because the enzyme is actually covalently attached to the matrix. Okay, so it's a chemical method. Other chemical methods of enzyme immobilization are cross-linking of enzymes. This is a lot more, if you compare with this one, this is a lot tighter arrangement, in the sense that the enzymes are cross-linked, as is more or less obvious from the picture itself. You compare this with this, you see that the enzymes are cross-linked with a functional reagent, which allows it cross-linking to the, so there is the matrix itself is a function reagent embedded in it, which will allow the enzyme to cross-link to it. As a result, it will be a much more tight arrangement, and then you can have a possibility where the enzymes, look at this, the bottom one here, where the enzymes themselves cross-link among each other to form the matrix. Okay, so this is the difference between this and this. Here, the enzyme is attached or bound to a functional reagent, and that's how the cross-linking is attained. While below, the enzymes themselves cross-link with each other to form the cross-linked matrix. So, these are a few examples, and if you go to some of the books, you will find plenty more examples, but just to give you a sense of how this chemically bound enzymes look like. Now, there are other kinds of entrapments or other kinds of enzyme immobilization, which are known as physical immobilization. And one example of physical immobilization is that you trap the enzyme in hollow fiber membranes. So, these hollow fiber membranes are really very thin cylinders, so to say. If you think of them, they are like a bunch of cylinders, like shell and tube heat exchanger, except that the tube side is really small. And so, you entrap the enzymes being small themselves, you entrap the enzyme within those hollow fiber membranes. And then you can have what is known as enzyme entrapment within the insoluble gel matrix. So, there is an insoluble gel matrix, and you physically entrap, there is no chemical bonding out here, and you physically entrap the enzyme, and so this is one other possibility. So, these are just a couple of examples that I am showing you for each type, and then if you are interested in a laundry list of the kind of chemical and physical entrapments that are possible, you can always go back to the book. Bailey and Olis is a good book to go back to anytime. So, but the point is, so there are several ways we can entrap an enzyme, but the question is that why would we like to entrap an enzyme? Why would we like to immobilize an enzyme? What do you think? To prevent the loss of enzyme, yes, that's a good point. And what else? What else could is a possibility? To make it, in a way it comes under what you said, to make it less susceptible to other kinds of reactions, right? Because you want a specific kind of reaction, for example, and if the enzyme is allowed to be attacked or by other kinds of reagents, other kinds of substrates, then your enzyme is sort of lost or reduced. So so that's the point, and here what I am trying to say is that enzymes are encapsulated in hollow fiber membranes or microcapsules, so that they are not susceptible to antibody attacks. Okay? So, this is a specific point, that not susceptible to antibody attacks, but in general you can generalize this and say that, so that they are not susceptible to attack from other kinds of substrates or reagents. Okay. What is a disadvantage? This is something that I really want you to try and understand. The advantage, fine, this is sort of easy, but what is the disadvantage of what could be the disadvantage of this entrapment or enzyme immobilization? Will be
active sites will be reduced.
Active sites will be well, yeah, not active sites wouldn't be reduced as such directly, because the number of active sites is still the fixed, but what, the accessibility to the active sites will be reduced. Yeah. So, why is that? What is the basic phenomena? That is a very basic chemical engineering thing that you are probably all aware of. What is the basic phenomena there? Yeah, but basically what will happen is there will be absorption is a part of what? Mass transfer. So, essentially there will be all, see, earlier the difference between this and the earlier thing is that earlier we had simple reaction taking place because it was dissolved and the substrate was in excess and stuff like that. But now what will happen is, because the enzyme, say let us go back to one of the pictures, see for example here the bottom picture you see. So, the enzyme is deep inside the matrix. So, for the substrate or whatever it is going to react with, to reach this, there is a lot of mass transfer resistance that it has to overcome. Okay. Even if it's, forget adsorption, even if adsorption is there, forget adsorption. First, there is a diffusional resistance that has to be overcome. Okay. Look at this. Here also, if the substrate is in solution, dissolved in the solution, there is still a diffusional resistance that is there for the solution to the substrate to overcome till it can reach the enzyme. Whereas, if the enzyme was allowed to dissolve freely into the liquid, then it could at any point of time be reacting with the substrate. So, basically the basic difference is that there is a lot of mass transfer resistance that have to be overcome. Okay. So, so what it says is increased mass transfer resistance and decreased efficiency of substrate utilization. So, of course, if there is increased mass transfer resistance, there is going to be decreased efficiency of substrate utilization, and encapsulated enzyme, digestive enzymes and so on. So, as I told you with the first example I gave you on the first day itself, I think that why are these enzymes used, immobilized enzymes? So, digestive pills, for example, if you did not digest something well, there are two possibilities. You can take a liquid enzyme, okay, these are like carmozymes and so on, like lots of liquid enzymes are there, and you can take a solid enzyme, which is like a tablet or a capsule. So, that is precisely the difference between a entrapped or immobilized enzyme in the solid form as opposed to the liquid form, which is a mobile enzyme. Do you see the difference? So, physically in terms of examples is the difference. So, if you take the same digestive medicine in liquid form, then it is a mobile enzyme. If you take it in the solid form, it is a immobilized enzyme. Okay. So, that is a basic difference. So, what we will try and understand first is that what are these resistances. So, because once you one of the things that you understand is that the basic kinetics of enzyme reaction still remains the Michaelis-Menten kinetics, right, which is what we studied. Basic kinetics still remains the Michaelis-Menten kinetics, but because of mass transfer resistances, the kinetics that you see now is going to be the observed kinetics that you see, this is a very important word to remember. The observed kinetics is going to be different from the intrinsic kinetics. Okay. So, a chemical reaction has two kinds of kinetics, and probably you have studied this in your reaction engineering course. One is the intrinsic kinetics and the intrinsic reaction rate, and the other is the observed reaction rate. So, why are these two different, the intrinsic reaction rate and the observed reaction rate? Because of what kind of limitations? Because of mass transfer resistances. So, the observed and the intrinsic kinetics are different because of mass transfer resistances. So, what we have to figure out. So, earlier the first chapter that we did, the advantage was that there was only intrinsic resistance, there kinetics, there was no observed kinetics. I mean, observed kinetics are, in other words, was same as intrinsic kinetics, right. So, the mass transfer resistances were not there. Here, because of mass transfer resistances, the observed kinetics is different from the intrinsic kinetics, and what matters to us is the observed kinetics. Okay. Because the intrinsic kinetics, intrinsic kinetics is a measure of the maximum possibility of reaction rate, right. So, but that is not of any use to us, it is important, but it is not of any use to us unless the reaction is actually happening at that rate, is not of any use to us. What we want to figure out is that at what rate the reaction is actually occurring, and that is observed reaction rate. So, most of what we are going to do in this chapter is to figure out the observed reaction rate, okay. And this reaction rate is reaction rate in the presence of mass transfer resistances. Have you done this in your reaction engineering course, this the effect of mass transfer on reaction undergraduate level? Okay. So, anyway, that is good. So, it is a new thing that we will probably try and do over here. So, is a concept clear that what we are going to do here, how is it fundamentally different from what we had done in the previous chapter? Previous chapter we looked at only kinetics and come up with pure kinetics. Here we are aware of the kinetics, we were aware that it is a Michaelis-Menten kinetics, we are aware how to measure those rate constants, everything we are aware of, but the point is that it is not of any use to us. We have to figure out what the intrinsic the observed kinetics is, and so we will take the intrinsic kinetics and try to see how mass transfer is influencing that and how mass transfer is reducing the observed kinetics. Okay, I use the word reducing because the observed kinetics is always going to be lower than the intrinsic kinetics. Okay, the observed reaction rate is always going to be lower than the intrinsic reaction rate. There could be one or two very exceptional cases, I might want to talk about that later, but otherwise the observed reaction rate is going to be less than the intrinsic reaction rate. Now, before we try and do that, let us understand that in the presence of mass transfer resistances, what are the kind of reactions that we have, the biological reactions. So, the first kind of reaction that we have is homogeneous reaction, right. We studied that in the chapter before, and then the end of last class we studied what kind of reaction? What kind of reaction did you study in the end of last class? Heterogeneous reaction. Okay. Then what else could be there? So, homogeneous reaction is the first kind of reaction that we studied in the first 4 or 5 lectures. Then the second thing is heterogeneous reaction. At the end of last class we looked at it, and we looked at what is the role that adsorption plays, and we also tried to understand what is the role that diffusion plays and so on a little bit. But much of this chapter itself, in the next 3 or 4 lectures we are going to do this. So, that is heterogeneous. And what other kinds of reactions are possible? When you are talking of reaction models, reactor models, okay. So, what other kinds of reactions are possible? So, number 1 is homogeneous reaction. Okay. So, you have the A and the B going in, and reaction is occurring. Okay. Then the second one is, say, a catalyst pellet. We took this heterogeneous reaction. So, which is, say, A. So, homogeneous reaction, the definition is that A and B are in same phase. This is A and B are in different phases. So, what are the processes here? The process here is essentially reaction. Okay. So, maybe some diffusion. The processes here is diffusion of substrate into matrix followed by adsorption of substrates followed by reaction followed by desorption of products and desorption of products and unreacted substrates, and then diffusion of products and unreacted substrates. Okay. So this is a homogeneous reaction and a heterogeneous reaction. So, two major kinds of reaction. Now, when we model it, we model a homogeneous reaction, the as such in a CSTR, you know how to do this, you have been taught how to do this. Heterogeneous also maybe you might have been taught. So, these are the processes that you have to describe or discuss or understand and quantify. Now, there is another kind which is not really a reaction type, but a sort of a model which is known as pseudo homogeneous reaction. What is a pseudo homogeneous reaction? Does anybody have any idea? What is a pseudo? What is pseudo homogeneous? It says not homogeneous, but pseudo homogeneous.
Reaction is not actually homogeneous, but it appears when it
Homogeneous, right? Reaction is not actually homogeneous, but we take it to be homogeneous rather. So, reaction is actually what? If it is not homogeneous, what it is? Heterogeneous, yes. So, reaction is actually heterogeneous, but taken to be homogeneous. Okay. Let us see, for example, you have these say in a catalyst bed or something. So, you have these different points, points of reaction. These are different catalyst pellets that are there. So, one way would be to look at it in a heterogeneous way. So, take each catalyst pellet and look at what is reaching this catalyst to diffusion, reaction, adsorption, reaction, desorption, diffusion, and so on. The other is you say, for example, you are lazy and you really do not want to quantify each catalyst pellet. There are thousands of catalyst pellets and you really do not want to quantify each catalyst pellet, or you do not even want to quantify a single catalyst pellet. So, what you do is you come up with a pseudo homogeneous model where you average out the reaction rate. Okay. So, this is average out the reaction rate. So, at each point you have a certain reaction rate, but you figure out that what is my total reaction rate in the system. Okay, what is the average number of pellets? So, you have say 1000 or 2000 pellets in there. What is the reaction rate for each pellet? Find out the total reaction rate divided by the volume, and you get the volume average reaction rate of the system. So, then you probably be able to say that. Okay, so, this is my RV. Typically, these are known as RV, which is RV bar, sorry, volume average reaction rate. Okay. So, this is a pseudo homogeneous. So, pseudo homogeneous is not really, I want to be clear, pseudo homogeneous is not really a reaction, but it is essentially a way of description. Okay. And the last thing that we will do, that I will show you here is known as a coupled homogeneous heterogeneous reaction. Okay. And this is very straightforward, this is not a form of description. A coupled homogeneous heterogeneous reaction is a coupled homogeneous heterogeneous reaction is, for example, you have the catalyst pellet out here. So, this is reacting. So, this reaction A plus B is happening on the catalyst pellet, right. So, this is a heterogeneous reaction, and then you have C in the bulk phase, and another reaction B plus C giving S is happening, and this is in the bulk phase, and this is a homogeneous reaction. Is it clear? A coupled homogeneous heterogeneous reaction is a reaction in which some reactions, a network of reactions in which some of the reactions are in the bulk phase or homogeneous phase, some of them are in the heterogeneous phase, and then you can have other kinds of things happening. For example, you can have this, and then you can have a reaction on the surface of this S plus P giving R. So, this is a whole network of reactions, and typically in real life most of the reactions are belong to this category, where there will be some reactions which are homogeneous. So, if you go and work in the industry and work with certain reactions, chemical reactions in the catalyst beds and stuff like that, that is always something that will happen. Why? Because maybe your heterogeneous reactions are the ones that are desirable, the ones that you want, but there will be always side reactions that will happen in the bulk. Okay. So, this is something that is very likely. So, this is the fourth kind of reaction, the coupled homogeneous heterogeneous reaction. So, now let us try and understand what would be the reaction rates and so on for some of these processes. Okay. So, next what I want to discuss is what is known as the observed reaction rate, and as I said that the observed reaction rate is different from the intrinsic reaction rate, right. It could be equal to the intrinsic reaction rate under certain cases. So, what we do is, when we talk about the observed reaction rate, we divide it up into different regimes. Okay. We divide it up into different regimes, and two of the regimes are the reaction limited regime, and these are names that you should remember, reaction limited regime, and another one is called mass transfer diffusion limited regime. Okay. And there is something that is in between, it is called intermediate regime, which falls between the reaction limited and the mass transfer limited or diffusion limited regime. So, what is a reaction limited regime?
Reaction rate is limited by
the slowest
Which is the slowest step?
reaction.
Reaction is the slowest step. So, you might have other kinds of, so basically it is mass transfer and reaction. So, whatever mass transfer, could be convection, diffusion, whatever. So, reaction is in this case reaction is the slowest step, right. So, that is called the reaction limited regime. Now, mass transfer limited regime is a regime in which mass transfer is the slowest step, and intermediate is that where reaction and mass transfer are equal in terms of their speed. So, in intermediate reaction, so how do we quantify these? The way we quantify these rates are through the okay. So, these are the three regimes that I discussed: reaction limited, intermediate, and diffusion limited. So, how do we quantify these? How do we figure out that what is the slowest step, what is the fastest step? How do we figure these out?
by knowing the numbers.
Yeah, what or numbers or what? Huh? Well, yeah, the Amcoller number is not really, but phi square, the Thiele modulus is the one, but forget the numbers. In a simple way, through time scales. Okay. So, time scales. So, time scales of reaction and diffusion and comparison. So, comparing the time scales of reaction and diffusion, and obtaining the time scales and comparing the time scales of reaction and diffusion. So, if I give you a first order reaction, for example, okay, what would be the time scale? The TR, let us call it. Okay. TR is a time scale for reaction. What would be the time scale? How do you write it? So, you have a reaction of A going to B, K first order. What is the unit of K first order reaction? Time inverse. So, what would be the time scale? One by K, right. So, that is my reaction time scale. And If it is a second order, say this is first order, A going to be K R A equals minus K C A square. So, if it is a second order, then what is the unit of K in second order reaction? You have to always look at this way, once you figure out what the unit is, what is the unit of K? So, second times molar inverse of that, right. So, basically, one of the things you have figured out is that when you try to figure out what the reaction time is, the rate constant should be there, should be a part of it. Okay. So, if this is K, if I write, then there is a the unit is, it becomes second times molar, right. So, you will have K C, you have to divide it by molar to get time. So, you put a K C naught. Okay. What is naught? Is some reference concentration. Okay. So, C naught is a it could be the initial concentration typically. Okay. So, again this is the unit of time. Now, if I for any nth order reaction, so this is first order, this is second order, nth order reaction. So, R A equals minus K C A to the n. Okay. I do not care what it is, any reaction, let us call it. Okay. How do you rewrite that? How do you generalize this? 1 by? So, let us say any reaction, I do not even know what that, whether it is nth order, simple elementary nth order or the complicated form. If I have any reaction, what would be my time scale for reaction?
Time inverse concentration to the power 1 minus n.
No, I am saying I do not even know if this is this, if say if this is not the form, so the form is K 2 C A to the power n minus 2, something like this. What did you do? The form is something which I wrote to the corner here. If the form is not a simple elementary form, it could be anything. So, what did you do? This is what you do. Okay. Is it clear? So, it's R C naught over R C naught. Okay. So, match that with this. So, in first order R C naught is K C naught and C naught in the numerator, it gets cancelled. So, you have 1 over K. Second order you had C naught over K C naught square. So, 1 C naught gets cancelled, you have 1 over K C naught, and in any order, this is not even nth order, any order, you can have C naught over R C naught. Is it clear? So, this is an important thing to remember. So, any reaction I give you. So, what does R C naught means? What does R C naught mean? Reaction rate evaluated at concentration C naught. Okay. So, R C naught is fine. So, this is a generalized expression for any reaction rate we got. Now, we have to figure out what is the diffusion time. So, just as reaction time involves the reaction rate, diffusion time should involve the diffusion we are talking of. So, it is specifically diffusion. Mass transfer could have convection effects and so on, but let us take the simple case of just diffusion. should involve the diffusivity. Okay, dm, let us say molecular diffusivity. Okay. So, do you have any idea what, any of you, what the diffusion time is?
N square
Yeah, that's correct.
N square by
Diffusion. So, L square, let us say, by dm. Okay. L being the local diffusion length scale. Okay. So, if you have a catalyst pellet, a spherical catalyst pellet, say L is the radius or the diameter, whichever, you can just use the diameter if you want. If you have a catalyst pellet which is like a slab, then L is the distance length along which it diffuses. Okay. So, this is now now so you got this, you got this. So, TR you got as this. Okay. Now, what would you like to do if you want to figure out if it is in the reaction limited regime? So, if it is in the reaction limited regime, then what happens? TR, what is the relationship between TR and TD? In the reaction limited regime, TR is much greater than TD. So, the reaction time is much greater than diffusion time, or reaction is much slower than diffusion. So, if I put it over here, what I got, okay, what I got here. So, C naught over R C naught much greater than L square over dm. Okay. Fine. So, which means L square R C naught over dm C naught is much less than 1, right. What is this? Do any of you know what this is? This is phi square. So, phi square equals L square. Okay. This is Thiele modulus, named after the very famous reaction engineer, chemical engineer, so to say, Thiele. Okay. So, this is my condition for reaction limitation. So, later on in this chapter when we do, and we will talk about this, that reaction limited regime. So, what we need to measure is phi square, the Thiele modulus. Okay. Now, there is, I will just at this point I will tell you that there is phi square is my and there is something called an intrinsic Thiele modulus, and there is something called an observed Thiele modulus. Can you tell me what the, so this is the intrinsic Thiele modulus, what the observed Thiele modulus is going to be? So, the Thiele modulus, that is the actual Thiele modulus of the particular reaction and the material, is different from the Thiele modulus that you observe when you observe experimentally. If you can tell me, or if you can think in the direction why that happens, then you will be able to tell me that what the observed Thiele modulus is. Why does this happen, first of all? Why does the observed Thiele modulus sometimes is different from the intrinsic Thiele modulus?
The rate we are considering is that is the actual reaction.
Right, good. So, the observed Thiele modulus is exactly the same thing, except that the rate here has to be the observed reaction rate, just as I told you, and it is on the screen now, if you look, that the observed reaction rate. So, the observed reaction rate is different from the intrinsic reaction rate, and therefore, you have the observed Thiele modulus can be less than the is typically less than the intrinsic reaction rate. So, in the reaction limited regime, the observed reaction in the reaction rate is it same or different or larger than intrinsic reaction rate. So, this is a reaction limited regime we are doing, okay, and phi square is the reaction limited regime is phi square is much less than 1, right. So, which means that T r is much greater than T d, or T d is much less than T r. So, when T d is much less than T r, what does it mean? That mass transfer resistance, and let us put kinetic resistance on this side. What is the relationship between these two? Kinetic resistance is much higher. So, mass transfer resistance is much lower. Why is that? Because mass transfer time is very small. So, if time is very small, then time is inversely proportional to resistance. So, if mass transfer time is very small, then mass transfer resistance is much lower. Okay. So, if mass transfer resistance is much lower, then what is the relationship between the observed reaction rate and the intrinsic reaction rate? Both are the same, right. So, let us go back to the screen for a moment, and you will see that observed reaction rate here for the reaction limited regime is same as the intrinsic reaction rate. Why? Because I explained that observed reaction rate is less than intrinsic reaction rate because of mass transfer limitations. Now, if there are mass transfer limitations are not present in the system, then the observed reaction rate and the intrinsic reaction rate are the same. Okay. So, let us go to the next one. What I want to do is the last one, the diffusion limited regime, and we have already done this. So, it will take us a few seconds to do. So, diffusion limited regime, again my T r is C naught over R C naught, my T d is L square over d m. In the diffusion limited regime, what means diffusion is limiting, right, which means that T d is much greater than T r, or diffusion time is much greater than reaction time. Fine. So, diffusion time is much greater than reaction time. So, L square over d m is much greater than C naught over R C naught, or L square R C naught over d m C naught is much greater than 1, which implies phi square is much greater than 1. Okay. So, by the way, just if I for a minute just do not want to confuse you. So, in the reaction limited regime limited case, my phi square intrinsic is going to be equal to phi square observed, right, because the reaction rate intrinsic and observed are the same. So, in the diffusion limited regime, this is my criteria. Okay. So, in case of, so if this is the case, phi square is much greater than 1, or in other words T d is much greater than T r. In the extreme limit of this case, what would be my rate of observed rate of reaction? Observed rate equals, so first case reaction limited regime we had that the observed rate equals the rate of intrinsic rate of reaction. The other extreme asymptote where the reaction is very fast as compared to mass transfer, what would be my observed rate of reaction? What would be the rate limiting step? First case, what was the rate limiting step? Reaction was rate limiting step. So, in the other asymptote, what is now? So, there are two things, there is diffusion and reaction. So, if diffusion is much slower than reaction, then what is the rate limiting step? Of course, diffusion is the rate limiting step. So, observed rate would be equal to the rate of diffusion in this case. Okay. So, if I can go back to the screen, you will see that. So, in the observed in the diffusion limited regime, the observed rate equals the rate of diffusional transport, and in the intermediate regime, the reaction rate is a function, the observed reaction rate is a function of the intrinsic reaction rate and the rate of diffusion. So, if you see here, when I say reaction rate, I mean the intrinsic reaction rate over here in the middle. So, the observed reaction rate is a function of the intrinsic reaction rate and the diffusion rate, and these are the most difficult things to actually calculate as compared to the other two, because the other two conceptually, once you make a sense that okay, it is going to be in the diffusion limited regime or the reaction limited regime, you directly know the rate. But in the intermediate zone, you have to calculate, and as you know, as things are, life is always difficult. So, you have to calculate, because most of the things that we deal with in real life are in the intermediate zone between reaction and diffusion limited regime. So, what we will do is we will start now with a problem that we want to do, and the problem pertains to what I just showed you, the picture that I showed you, this one. So, this is for example, a enzyme which is bound to the matrix, and how does this diffusion mechanism happen? How does the diffusion and reaction mechanism happen? So, we have studied the mobile enzymes in the first few lectures, 4 or 5 lectures, and that was a pure reaction, but now diffusion plays a major role in that. So, we need to try and understand that how this happens. So, what we will do is in the next part of this lecture is try and understand how this happens. So, we consider enzyme which is covalently attached to a water insoluble matrix as receptors and acts as receptors, and the substrate is dissolved in the water or plasma, whatever it is, and their assumption is that there are no convection effects. Okay, this is water or plasma, let us call it. So, this is how it looks like. So, this is the my matrix, and these are the enzymes which are, so this is the symbol for receptors, by the way. So, these are the enzymes, and the red ones are the enzymes, and they are attached to this matrix by being bound to receptors, right. Now, so the substrate is dissolved in the surrounding CS. So, what we are trying to figure out is that what is the reaction rate, observed reaction rate, so to say, because the intrinsic reaction rate is something we know, but we have already understood that because of mass transfer limitations, the observed reaction rate is going to be less than the intrinsic reaction rate. It is not going to be that. So, the problem that we are going to face first of all is that any kind of, in this chapter, that is a problem we will always face, is that any kind of analytical solution or analytical quantification that we try to do would be limited by the fact that the intrinsic reaction kinetics that governs the interaction between the enzyme and the substrate is what type? It is the Michaelis-Menten kinetics, right, which is by default non-linear in nature, right. So, any kind of analytical effort or analytical quantification that we try to do in this class is going to be limited by the fact that it is Michaelis-Menten and therefore non-linear, and non-linear systems cannot be treated in nonlinear ODEs cannot be treated, or PDEs cannot be treated so easily. So, what is the way out? What can we do about this? I mean, we can leave it and not do it. We can do it quantitative, that is, we can compute it, but when we compute it, we do not get a sense of it. The advantage with analytical solutions, you can solve it and you can get a sense of what is happening. So, what would be my other possibility? And we already did that, if you remember, something like this in one of the earlier lectures.
At the extreme,
two extremes, right. So, you try and figure out what you can do at the two asymptotes of what? Large concentration of the substrates and small concentrations of the substrates, and the limit of large concentration of the substrate, the Michaelis-Menten kinetics tends to become 0th order, in the limit of small concentration tends to behave as first order. So, the actual order of the Michaelis-Menten kinetics is a fractional order between 0 and 1, right. So, we get the two asymptotes, and once we get the two asymptotes, so we figure out how it is going to behave at first order, how it is going to behave at 0th order, and the real nature is going to be limited or is going to be bounded by these two behaviors. So, that is the strategy we will take, that while we understand that we cannot, except for one little case later on, while we understand that we cannot do it for all cases for the nonlinear kinetics, we will do it for the linear and the 0th order kinetics, and then have our solution, actual solution, be bounded by these two solutions. So, that is exactly what we will do, we will split it up. So, here what you see, again going back to the picture. So, this is my matrix and Re is the radius of the enzyme matrix, D is the diffusivity of the matrix, and your receptors are out here, which and your enzymes are the red dots out here, and the receptors are bound to it, and the substrate is in the plasma or the water, whatever it is surrounding, typically say let us say plasma if it is in the biological system. So, what do you think, what would be the process here? Let us talk about the process first before we try and do any calculations. What do you think would be the process? How are things going to happen? So, the enzyme is sitting there tight, right. So, it is covalently attached to the matrix and it cannot move, fine. Why cannot it move? It can move, the matrix itself can move, but it is very hard for this. The matrix is, if you consider the matrix as compared to the water, the density of the matrix is much higher than the density of water or the plasma that surrounds it. So, the possibility that the matrix itself will move is very, very little. The reason being that we have already neglected convection effects, right. We already said that convection effects are negligible. So, if that is the case, then the possibility the matrix will itself will move is very little. So, what is the other possibility? So, they have to come together, the enzyme and the substrate has to come together. So, the enzyme cannot go to the substrate will come to the enzyme, right, is it clear? So, the substrate will come to the enzyme before it reacts. So, how will it come? It will come through what is the process? Simple diffusion, right. So, that is the mechanism that we have to try and model. So, our mechanism is that the substrate reaches the enzyme through diffusion, and once it reaches the enzyme, we neglect absorption and all that stuff here. Once it reaches the enzyme, it reacts with the enzyme. Okay. So, it is a simple process, but it is a two-step process that you have to kind of model. So, I am not sure if you have done this. Have you done this in any reaction or anything? This probably not. Okay. So, I will go slowly through it. So, essentially this two-step process, one is diffusion of the substrate to the enzyme followed by reaction. Where is the reaction going to take place? You tell me now. Let us look at the picture. And so, this is a matrix and you have the receptors bound on the surface, okay, and the enzyme is this red dots on the receptor. There is nothing, no enzyme inside, remember, it is a enzyme on the surface. You can have encapsulation, this is not encapsulated enzymes, right. These are immobilized enzymes, but immobilized on the surface. So, you can have 2 or 3 different kinds of things. We can have immobilization which is inside the matrix, right. You can have immobilization on the surface of the matrix, and you can have immobilization which is both on the surface and the inside, encapsulation plus immobilization on the surface, right. So, this if we go back to the picture, so this is my immobilization on the surface. So, where is the reaction going to occur? At the surface, right. So, the reaction is, the reactive binding between the substrate and the enzyme occurs at the surface, and we will do, as I said, 2 extreme cases of large concentration of surface and large concentration of substrate and small concentration of substrate. Okay. So, look at these 2 cases. So, this is my Michaelis-Menten kinetics in the limit of dilute concentration solution of CS, that is small concentration. CS is much smaller than Km, and my RS is K1 times CS, where K1 is the first order, it looks like a first order rate constant, and it is R max over Km. Clear? Okay. So, I want you to understand that though we will deal with first order and zeroth order kinetics, but these are limits of the Michaelis-Menten. We are not randomly or arbitrarily working with first order and zeroth order kinetics. This is something that you need to remember. The second point is that for the concentrated solution, that is CS much larger than Km, the RS is the maximum, it is the zeroth order kinetics, and RS is the maximum reaction rate, right. Okay. So, we will do both these cases. I am not sure, probably we will not finish today, but we will continue. So, let us do the dilute solution case, which is a small low concentration of CS, and what we take is a reaction diffusion model. So, what kind of let me ask you first that what kind of the reaction diffusion model, fine, but what excuse me, what kind of geometry are we considering here? Yeah, but remember that you are not solving for the matrix itself. Inside the matrix nothing is happening, whatever is happening is outside the matrix. Okay, that is something you need to remember. Where are you solving? You are solving outside in the plasma or in the water, is that clear? Okay. and your matrix is spherical. So, what kind of coordinate are you going to take? Matrix is a sphere and you are solving outside the matrix. So, what kind of coordinate would you take? It is best to take a spherical coordinate. Why? Even though you are not solving, this is something dichotomy I want you to understand, that even though you are not solving inside the matrix, you are solving outside the matrix, still it is better to take a spherical matrix, spherical coordinate. Why is that? Because because of the boundary conditions. See, the boundary conditions is on the sphere, right, and you have to, at the end of the day, you have to implement the boundary conditions on the surface of the sphere. So, the boundary condition is on the sphere. So, in order to be able to implement it with maximum ease, you better have a spherical coordinate. So, when I write, if I ask you to write this diffusion reaction equation, you probably do not remember the diffusion equation, I am sure, for each of these coordinates. Do you remember? No, I think. So, I will ask you to do that, but let me okay, first. So, this is diffusion into Laplacian of. So, this is for the substrate, we are drawing for the substrate. Okay. So, this is my matrix, okay, with the enzyme stuck out here, and the surface is coming the CS, the substrate is coming from wherever to this. So, we are drawing the we are writing the diffusion equation for the substrate. So, this is my Laplacian, okay, equals something. So, remember I am writing my equation, I am telling you again and again, I am writing my equation outside the sphere. So, what is my, this is the diffusion part, right, diffusion times Laplacian of CS. What would be my this side, right hand side?
Reaction.
Everybody thinks it should be reaction. It is not going to be reaction, it is going to be 0, because I am writing, this is what I am trying to tell you, that I am writing my, I am trying to solve outside in the water or in the plasma outside, and no reaction is occurring.
But it is approaching the surface.
No. I'm so wherever it is, no, not from approaching the surface. I'm my domain is from anywhere to the surface. So my surface is RE, okay, and my domain of interest is 0. Sorry, RE less than equals R less than infinity. So it's approaching from anywhere in the solution, in the solution to the surface. So that is my domain of interest. So during this area or in this domain of interest, there is no reaction that is happening. Okay, all reaction, that is what I tried to specify before, that all reactions are happening on the surface of the matrix. Is that clear to everybody? Is that clear? So all reactions are happening on the surface, and when I am writing my equation, the domain of interest, there is no reaction that is happening. Okay. So if I am to write this, yes.
We will include the reaction in the boundary condition.
We will include the reaction in the boundary condition. I will come to that, but just going a little slow. So if this is what it is, then in the Cartesian coordinate, how do you write this? I am just writing it for the sake of you in all coordinates. So one time, so that you remember this and I do not have to go through this again and again. So ds into, right, in the cylindrical coordinate, and if I am to do a 2D, this is 1D, and a 2D would be ds into okay. Now let us write it in the cylindrical coordinate. So 1D would be in radial, only in radial if I am writing. Do you know what it is? Do you remember the Laplacian? Okay. This is 1D, and then 2D would be So, ds times 1 over r del del r of r del c del r times ds times del 2 c del z square equals 0. Fine. In the spherical coordinate, we typically do not have 2D, we have either 1D or 3D, right, because if it is asymmetric, it is asymmetric in both the azimuthal directions typically, and if it is symmetric, you have only r. Is it clear? So, in the spherical coordinate, if it is symmetric, that you only have r, and if it is asymmetric, then you have r, theta and phi, all three. Okay. So, in the spherical coordinate, what is going to be? So, 1 over r. Do you remember, one of you, any of you? Okay. So, this is my equation. So, this is what I have if I go back to the screen, and what I will do is that quickly I will, we are probably running out of time today. So, I will just give you the boundary conditions because we are at it. So, as we discussed that one of the boundary conditions is that the reaction is occurring on the surface. Okay. So, what you have? So, R equals R e. So, this is my boundary. Okay. This is, what did you have? Just tell me conceptually, maybe we will write it a little later.
Rate of diffusion is equal to mass transfer rate is equal to reaction.
Very good. Yeah. Mass transfer flux equals reaction rate. Okay. So, what is your mass transfer diffusion flux? Mass transfer flux is same as diffusion flux. So, what is it that going to be? Minus 4 pi r e square if I am to add the surface area times, very simple, d s times dc, let us say dcs dr at re, right. So, this is my diffusional flux equal to reaction rate, which is K1 times Cs. Is that clear, everybody? So, my mass transfer or diffusion flux. So, this is my boundary condition BC1. Okay. So, this is my governing equation, and my last my last boundary condition is that. So, this is my surface, let us say, and this is Re. My last boundary condition is very far away from this, the concentration is a constant. So, Cs equals C naught, Cs naught, very far from the matrix. Okay. So, very far from the matrix is a constant, and well, close today because we have completely run out of time. So, the boundary condition at R equals Re is given by this, and the other boundary condition is very far, that is R going to infinity, the substrate concentration is a constant given by Cs naught. So, we will start in the next class from this place and continue. So, thank you for your time.